Okay, you guys, so for this lecture, we are still continuing organometallics, and I want to continue with hapticity, which is what we left off in lecture number 6. And so if you remember, hapticity is denoted by eta and a number. And so let me go ahead and write that down. And so you use the Greek letter eta, and the number that I'll highlight is the number of atoms bonded to the metal. And I gave you a couple of examples with respect to hapticity, and it was also on your problem set number 3, part 2. I just want to go ahead and just review it really quickly. And one of the examples that I gave you was the following allylic system, where in this case, you can see that the metal is bonded to one carbon. And so this is eta 1 carbon bonded to metal, okay? You can also have the allylic system bonded to the metal through the pi bonds, and this is eta 3, i.e. 3 carbons bonded to the metal. Now, what I want you to note that in this case, 2 electrons are bonded to the metal, right? And so in this case, you have not only the 2 electrons, but you have the double bond as well, bonded to the metal, for a total of 4 electrons. So this is 4 electrons bonded to the metal. This is 2 electrons bonded to the metal. So the hapticity really tells you the number of electrons that the ligand is donating to the metal, okay? So those are the first couple of things. And then finally, the oxidation state of the metal. The oxidation state of this system is -1, and the oxidation state of this system is also -1. That's the only thing that they have in common, is the oxidation state, because regardless of how it's bonded, whether it's through a single bond or an allylic eta 3, it's still -1. The electrons belong to the ligand, and regardless of that, it's still a -1, okay? For the ligand. This -1 is for the ligand. Okay? So you have to be really careful and take a look at the eta number. The other example that I gave you was of cyclopentadienyl, and it was also on your problem set. And we introduced it as follows, where I told you this cyclopentadienyl, just like before, you've got 2 electrons. This is eta 1 carbon bonded to your metal. The ligand is donating 2 electrons. Okay. I also gave you a different example. This is eta 5. It's still a cyclopentadienyl, but now notice that this structure has resonance. And because it has resonance, you have the flow of electrons all around your ring. And so the entire 5 carbons can be bonded to your metal. So in this case, 5 carbons bonded to my metal. The ligand is donating, in this case, 6 electrons. Because it's the entire 5 carbons, there are 6 pi electrons, and so that's what's donating to my metal. Please notice that regardless of how it's being bonded, it's still a -1 charge from the ligand. And then finally, the last example that I gave you was the fact that not all 6 pi electrons have to be donating to the metal. It can be an allylic system as well, right? Just like the above example. Notice how you have this type of allylic system. Same thing here. You can use the allylic system to bond to the metal. In this case, this is eta 3, just like up here. Exactly same example. Just like before, in eta 3, there are 3 carbons bonded to the metal. The ligand is donating 4 electrons, just like before. And just like before, it has a -1 charge coming from the ligand. Okay? So these are the various ways that cyclopentadienyl can bond to a metal. Now, I introduced this in problem set 2 in the sense that I told you that cyclopentadienyl is typically denoted as CP. Okay. Now, usually in front of the CP comes the eta. So in this case, this would be eta 1 CP. This would be eta 3 CP. And this would be eta 5 CP. And so what they all have in common is clearly the CP, the -1 charge. It's just how it's bonded to the metal, or how many atoms are bonded to the metal. Okay? And so I just want to go ahead and finish up a few examples. And we'll do the same thing that we did for lecture number 6, where we talked about the oxidation state of the metal, the number of d electrons, the total count, and whether our complex is saturated or unsaturated. So example number 1. And so, of course, you need your periodic table, and I'll always provide that for you on an exam. We'll talk about the oxidation state of the metal, number of d electrons, the total count, and is it saturated or unsaturated? Okay, exactly like we did for lecture number 6. Okay, and so in this case, you do need to remember your ligands, right? And what they contribute to the metal. And if you remember, phosphorus ligands are neutral, but our halogens and our allylic systems are -1 charge, which means that this is a palladium 2+ to counterbalance that charge. How many d electrons do we have? Well, palladium alone, when it's 0 oxidation state, is d10 electrons. But when it's palladium 2 plus, there are D8 electrons. So in this complex, the palladium is coming with D8 electrons. What's the total count? Well, palladium, like I just said, is coming in with 8 electrons. The triphenylphosphine, not the triphenylphosphine, excuse me, the trimethylphosphine is coming in with 2 electrons. The chlorine minus is coming with 2 electrons. The allylic system is coming, let me draw this dash, is coming with 4 electrons for a total of 16 electrons, and it is unsaturated. Okay. And so obviously when it's unsaturated, the complex can continue to do reactions. If it's saturated, it can't move forward. And we'll see this as we're going through the various types of reactions that we're going to talk about later on. Okay, let's do another example. Oh, excuse me. Okay. So we've got this titanium system. Please notice that these are all CPs, right? Regardless of how they're bonded to the metal, they're all CP systems. And so because they're all CP systems, there is a -1 oxidation state for each one of these ligands, which means that the oxidation state for the metal is titanium 4+. Okay. On the periodic table, if you go to titanium, when its oxidation state is, when its oxidation state is 0, it has D4 electrons. But not surprisingly, when it's 4+, it is now D0. So it's coming in without any electrons whatsoever. The total electron count is, for titanium, again, 0 electrons. There are 2 cyclopentadienyls that are 801. And this is 2 electrons each for a total of 4 electrons. 2 electrons here, 2 electrons here, 4 electrons. And then we have 2 cyclopentadienyls, eta 5. Each one is coming with 6 electrons for a total of, 12 electrons. And the total is 16 electrons again, and it is unsaturated. We'll do a few more examples before we move on. Okay. Again, carbon monoxide ligands are neutral, but our cyclopentadienyl and our carbon systems each come in with a -1, which means that my iron has a 2+ charge. When its oxidation state is 0, it has D8 electrons. When it's 2+, it's got D6 electrons. Just like before, we'll calculate the total electron count. Iron 2+ is coming in with 6 electrons. There are 2 carbon monoxides. That's a total of 4 electrons. There's 1 alkyl group, and that's 2 electrons. 1 cyclopentadienyl, and it's eta 5. There are 6 electrons. And in this case, the total electron count is 18 electrons, and it is saturated. Okay. I'll just do a few more, a couple more. This one's a little intimidating, but I'll show you how to approach it. Okay, so iron has 3 neutral ligands, right? So it does have the cyclopentadienyl, which is a -1. So iron must have a +1 to it to counterbalance that. But please notice that the net charge is +1, right? And so you have to take that into account as well. And so in this case, again, I have iron 2+. It's the +1 to counterbalance and the +1 as the net charge as well. So just like before in our previous example, in this case, we have D6 electrons. If we have D6 electrons, each carbon monoxide is contributing 2 electrons, just like before, 4 electrons. The one cyclopentadienyl, 8 of 5, is contributing 6 electrons, just like before. Now, in this case, we have our alkene. It's neutral and it's contributing 2 electrons for a total of 18 electrons. And it is saturated. Okay. And then finally, I'll finish up with this last example using a carbene system. And you had a carbene example in your problem set. I think it was problem 1B, if I'm not mistaken. And instead of drawing out the carbon monoxides, like I did here, I'm just drawing out CO. Okay. So notice how in this case, all of these ligands are neutral, right? Carbon monoxide is neutral. And if you remember, carbenes are also neutral. So in this case, the oxidation state of chromium is 0. And because it's 0, it has D6 electrons. And so let's do the total count. 6 electrons for chromium. There are 5 carbon monoxides, 2 electrons each. That's 10 electrons. So you can see that we're already getting to 16. And then finally, our carbene is 2 electrons, which makes sense. You should have 18 electrons. So you cannot go over 18 electrons, just like the octet rule, right? The take-home message is cannot go over 18 electrons. You can, of course, be under. There are systems that are 12, 14, 16 electrons, can be under 18 electrons. But you cannot go over. If a complex has 18 electrons, it will not do anything. It can't do chemistry. The other thing that I wanted to mention is that you cannot have an odd total electron count. Just like you can't have 7 electrons around a carbon or 5 electrons, an odd number, you can't have an odd total electron count you're saying it's a radical. So if it's odd, it's automatically wrong. You've calculated something wrong. You have to go back and fix that. Okay. Okay, this is a quick video because it's just a quick review. So I'll stop here for this part, and the next part I'll start introducing organometallic reactions.